So now you've made your regression model. Now let's go through and assess that model. So remember, the assumption of the regression model is that the response variable is made out of two pieces. We have our constant plus our predictor variables, which are deterministic, and then we have our error responses, which should be random, giving us the linear regression model of y equals beta naught plus beta 1x plus e, where e is our normally distributed error term, and it doesn't depend on any of the values in our explanatory variables. So when we look at our residuals, we're looking to see that there's not really any explanatory or predictive information in the error portion of the model, because the residuals really are supposed to be your error. So intuitively, the deterministic portion of the model should be explaining or predicting your response variable with nothing left over but randomness. And so if there is, we have some explanatory or predictive power in that error, then our model doesn't have all of the components needed in it, and it was overly simplified. Our residuals should be random. They should not be systematically high or systematically low. That tells us we have some bias in our model if that happens. We should also see relatively a normal distribution when we're looking at our models. So when you're assessing your plots, you can look at a PP plot, which is called a probability plot or percent plot for your p-value. And basically it's looking at how closely those two data sets agree with each other. And so it's going to plot the two cumulative distribution functions against each other in that PP plot. The QQ plot is more widely used, and it's typically referred to as the probability plot, but it's the same concept here. When we're looking at our models and we're looking at our residuals, a lot of times you'll look at your residual value and plot it against what your fitted value. Here we don't see any pattern in these residuals. They're not systematically high, they're not systematically low. There's really no explanatory power in here. So this would be an example of some good residual results. Here we see a clear pattern of the residuals in our results, so we would definitely see that we have violated that assumption of the model. When we're looking at our residuals and we see a non-random pattern, typically that's due to missing variables, or we have a higher order term of a variable, meaning that maybe instead of just having an x, maybe we need an x squared. Maybe we're missing interaction terms, so instead of an x1 times x2 kind of thing, or you might have a certain amount of autocorrelation, which has a time dependency in your residuals. One thing to keep in mind is that, all of our models are useful, but some are not as useful as others, right? So all models are wrong and some are useful, according to George Box. When we're assessing our model, we also look at the goodness of fit. And so that R squared is looking at the variance explained. So it's going to be the proportion of the variation in the dependent variable that's explained by the combination of predictor variables in your regression model. And here you can see a bunch of the different calculations for it, which I'm not going to make you do. But basically, one thing I do want you to keep in mind is if you take that square root of that R squared, we're going to go back and have that correlation coefficient when we look at the correlation between x and y. The only problem is because we're taking a square root, we don't know if it's a positive or a negative relationship. Here you can find that calculation for a root mean squared error, but basically it's to the regression line as the standard deviation is to our average. So it's just kind of giving us that little error bars as we look around our regression models.